Thank you so much, Dr. Pringle and Dr. Baird, for those warm words. Hey everyone, I'm Shashank, and today I'm talking about my thesis titled Tracking Human Movement Indoors Using Terrestrial LiDARs. And my committee members include Dr. Thomas Pringle, Dr. Timothy Baird, and Dr. Todd Ogle. Thank you so much for being here today. So starting off, talking about indoor spaces, the average American spends 87% of their time inside building spaces. But geographers do not look into these spaces as much as they look into outdoor spaces. All the surveying and mapping of the outdoor spaces has revolutionized so much over the years. But when you are talking about indoor spaces that are as important, those efforts seem a little bit less applied to. So whenever we're talking about surveying and mapping for indoor spaces, traditional surveying equipment fall short. They do not work as well as they do in outdoor spaces. Talking about like simple equipment such as theodolites and toll stations, those are based on line of sight operations. And inside buildings, there's a lot of furniture, pillars, and a lot of clutter that do not allow these instruments to work well. Talking more about these available technologies, GPS signals, those are something that have revolutionized outdoor mapping over the last few decades. But when you're talking about indoor spaces and GPS signals, they either don't work very well or they do not work at all. Whenever you are trying to receive GPS signal inside buildings, those are either totally cut off or like even the signals you receive are partial. So whenever we are talking about indoor maps and models, the closest models we have include building information models up to the left and CAD drawing, which is there's an example of it on the right. So just looking at these are mostly constructed for construction phase where you can look at the physical structures or the physical components of a building. But the GIS inside building spaces are not even modeled in these drawings and models. The interconnected relationship between different structures are not well shown in these models. Over the last few years, a lot of development has been seen in high resolution data collection. And this is an example of a LiDAR-based GeoSLAM, and this is a model of Wallace itself. And you can see how LiDAR enables looking inside buildings in such high detail, in such fine detail. You can look at every room, you can look at all the components inside the room, and this is such a fascinating thing that you can look inside a building on like multi-floor basis. This enables us to create models of 3D indoor spaces. And a fairly popular topic in the recent years has been digital twins. Digital twins are basically a virtual counterpart of any physical structure. And we can just see from this schematic diagram that a digital twin tries to model a physical structure as it is and also tries to establish the relationship between components. And just to give a basic definition of digital twins, it's a physical structure, but in a virtual environment. This is created so that you can visualize the aspects of the physical structures, as well as simulate and test out things without affecting the real nature of the physical structures. And a digital twin could be of a building. It could also be of something like a vehicle, a Cybertruck, for example. But one key thing that's missing in digital twins, and when we're talking about buildings, and one essential part of buildings is people using it, and humans are one of the major missing elements in an available digital twin. So this is a picture of people occupying a lobby space of a building in Virginia Tech, and you can see the building is actually made for people to use it, and a lot of people are sharing the same space and developing relations with the building as well as interacting with each others. But what do we do to integrate the human aspect of a building inside a digital twin? And if we're trying to collect data of people into digital twins, one key thing is I don't think any of us wants always to be observed, because we are people and we need to have privacy. And whenever we're trying to collect data about people using buildings, privacy consideration is the main thing. We do not want to violate anyone's privacy while we are trying to model the space. And this is a big thing. So the biggest question during our research was, whenever we are trying to represent individuals in a digital twin, how can their privacy be protected? Our solution to that were LiDAR sensors. So this is a graphic that kind of shows what I'm talking about. On the left, I'm trying to show how a space is modeled using a camera. And you can see that the cameras and available RGB sensors, what they do is they basically model a space, but also show identities of people. And I just talked about how privacy consideration is a major factor. Change that to a LiDAR sensor, it basically does the same thing, captures the essence of the space, but obscures the identity of people. You can basically see the same physical structure, people using it, but you do not know who is using that space. And that's a major development over collecting data of people. This is a snapshot of people using a particular space, but it's LiDAR collected. And now you can see that this shows there are some people in that space, but you don't know who that is. And that's a major development over by the use of LiDARs. So we started off with trying to create a digital twin. This is a snapshot of the first floor of a building at Tech, and this is based on LiDAR data acquisition. And you can see this is a model of an indoor space, but thinking about it, people are not static unless they are in a thesis defense, but people are not static. People tend to move around, and people tend to interact with each other, interact with the resources available in that space. And we thought about how any indoor space is dynamic in nature. So a digital twin cannot be a digital twin of people if it's not dynamic. And this is what our data looks like. It's a dynamic stream of people using a space. So you can see just by eye inspection that you realize people move a lot. They are like small ants in a space, and you can see people interacting with each other, people interacting with furniture. They also move the furniture around a bit to serve their purpose. This was pretty fascinating. When I saw this for the first time, I was usually amazed. So dynamic digital twins. And talking about building spaces and dynamic digital twins, one thing I just talked about is like how much people move inside building spaces. And the project I'm working on is a part of a larger NSF funded project on building ecology. And we are trying to think about how is a building space used over the span of a certain time. Talking about an academic building, a semester is a key period in a college, and people tend to do repeated set of activities at the start and at the end of the semester, but those have specific patterns. The activity increases and decreases and increases again based on the time of the semester. And this is a small effort to understand what those patterns are. So this is a schematic diagram of like what an indoor space is to us. So we basically design and create indoor spaces, and those are created with a purpose in mind to serve the users using it. If it's an academic building, it's for the purpose of students and faculties, or like anyone else who is using it. Another building might have a different purpose. So to fulfill that purpose, we scatter some resources in those spaces to fulfill those purposes, and those resources are shared by users of the building. And as they use it, they tend to get attached to the resources, they bring memories out of it, and that's when a vacant space becomes a place with memories and attachment. So the placemaking is a major agenda of this project. So to fulfill these objectives, we looked at a building at Tech. If we have not been there, this is what it looks like. It's a beautiful building. It's called the Creativity and Innovation District Living Learning Program at Virginia Tech. This is how it looks from the outside. The building is a mixed-use building in the sense that it's academic as well as a residential building. Going through the different spaces in that building, the building has a lot of spaces. Talking about a maker space where people come, explore their creativities. It has got outdoor classrooms. It has got community assembly where people come around, interact, and also living learning events are conducted there. The place also has meeting spaces, performance halls, and residence halls. The building is home to around 600 undergrad students. So we looked at the first floor of this building, which is a shared space, to understand how the dynamics of this space is. So the study area for my research was the first floor of the CIT building. And the first floor is a fascinating space. It has got a community assembly, as I showed a picture of. It has got a layout of furnitures, and it has got a stairs that goes to the second floor. It also has an exhibit space to the right of the space. So this is kind of the layout that I was working with. And the animation or the digital twin I showed you will also like be of the same shape. You'll see the same shape all the time. So To collect data of that space, what we did was we implemented and logged 11 of these Blickfeld cubes into that area. And these are looking inside the building so as to create a full 3D layout of the building. I'll refer to these sensors as Blickfeld cubes, and each of these Blickfeld cubes transmits around 2 megabytes of data per second. The Blickfeld cube allows us to like play with parameters to serve our purpose. And for now, we have the Blickfeld cube set with a field of view of 72 by 30 degrees, a refresh rate of 2.4 hertz, and a resolution of 230 scan lines. The data is transmitted through Ethernet into a computer, and we can use Python to decode the data into usable format. Time aligning the different sensors is available through network time protocol and precise time protocol. And talking about the data, we managed to collect 155 gigabytes of data per day per sensor. That amounts to 1.7 terabytes for all 11 sensors. And all of these data are not totally collectible because I told you we collect 1.7 terabytes of data per day. So what we are doing is we are trying to process these LiDAR data into different formats. And the first format I'm showing is a full 3D LiDAR point cloud. This is what it looks like when you are looking at that space on a whole 3D scale. And the data is collected at a frequency of 0.1 hertz. And for a day, it amounts to 13 gigabytes. The next format we are logging it as is an orthographic projection of the same point cloud, but with the floors removed. And this is an example of what a raster looks like. We are logging these rasters every second, and the data amounts to 8.6 gigabytes per day. Blickfeld is the company that made those sensors, and they also have their own system of collecting and logging data. So what Blickfeld provides is a LiDAR perception software called Percept, and it records logs of any moving object within the full 3D point cloud. And these data are logged as JSON files, and this is an example of what a JSON file looks like for that space. It's a standard format, but pretty difficult to interpret. But when you work with Python on these, you can basically convert these into a vector file. That's mostly common in geography and GIS. And these are the trajectories of people moving in that space over a certain period of time. Other formats include, from those orthographic rasters, we aggregate those into NetCDFs, which is a very commonly used format for meteorology, but we are applying it here. And this is an hourly summary generated from one of those NetCDFs. It kind of talks about like where a lot of activities occurring. The one on the right is an animation made from the orthographic rasters, and I showed you in a previous slide. So we talked about building a digital twin. We talked about the dynamicness of it, but how do we detect human movement in those digital twins? That's a question I was trying to understand. And for understanding this question, we tried a couple of methods. So the first one I am talking about is the deep learning YOLO V5 model. So I've got a flowchart of how this model worked. First, we basically took a bunch of data and split those into a training set and a test set. For my case, it was 80% and 20%. 2,880 frames were manually labeled with people in them and used as the training data to train the deep learning model. And the 20%, the remaining 20% was used for performance evaluation. The second model was based on OpenCV, and I used the most common OpenCV packages. First was background subtraction, and the second was frame differencing. Both of these methods were pre-processed to reduce the noise. And for background subtraction, a common background was modeled from a significant number of frames. And each frame was then subtracted from that background to detect moving objects. Similarly, for frame differencing, like consecutive frames were subtracted from each other. And if an object was there in the first frame and not in the second frame, it was counted as movement or like detection of an object. The third model I am talking about is Blickfeld's LiDAR perception software, Percept. So this is a bit different from the other two in the sense that it uses the whole 3D LiDAR stream, and it uses the mean shift algorithm to identify features moving in the point clouds. And it logs those as JSON files. I just mentioned that I had trained the data for deep learning. This is a small animation of how I'm training the data sets. So I loaded all the frames and I manually went in tried to identify people within those LiDAR streams and manually label them. It's pretty difficult to identify people in a single frame, so I occasionally had to go back and forth between consecutive frames to see if those were actual people-like movements. So this is an example showing me doing the same. And the deep learning model was trained on this, and 20% of these were used as the validation frames. So here I'm showing an example of how my deep learning model worked. You can basically see what you knew is being detected by the computer in those red boxes. So talking about those red boxes next to the boxes, so it has a word people in there. That's the class I'm training it for. And the number next to it is the confidence interval of like how confident the deep learning model is based on the detection. It works pretty well. One small section I want your attention to be is near this furniture area, where you can basically see that there are people near that furniture, but the computer does not do a good job of detecting it because as we obscure the identities of people, it kind of aligns with the furniture. Next up, OpenCV's background subtraction. You can see in green boxes that OpenCV also does a fine job of detecting people. And this is done by modeling a common background in 500 frames for our case. So it takes 500 frames and models a common background, and every frame is subtracted from it. The next approach is the frame differencing from OpenCV. So it basically subtracts consecutive frames to identify what was there and what is not there now. So this is an example of what the results look like. In blue boxes, you can see detections, and it basically applies differencing between consecutive frames. The third model I talked about in the method slide was Blickfeld's Percept, and here is how it works. So this is a real-time 3D live stream of LiDAR. And Blickfeld's Percept uses mean shift algorithm to identify what's moving by detection of clusters in the point cloud. So you can see that these red boxes are what Percept thinks are objects moving within that space. And most of these are people within that space. And I showed you the JSON file of what the data is logged as. We can basically post-process the Blickfeld's Percept data to just extract X and Y coordinates of objects detected. And this can also be visualized similarly to the other models. To compare the models and see which perform the best, what we did was we took 20% of the manually labeled frames and treated those as ground truth. So I'm comparing the detections from different models to the manually labeled frames. And to do that, I used the traditional metrics for performance evaluation. Precision, recall, and F1 scores are like common image classification performance metrics. And this is the mathematical relationship of true positives, and false negatives to understand precision, recall, and F1 score. So I'm going to compare the three different models in this next slide. And this is the chart that's going to show you. On the y-axis, we have the performance metrics, and those include precision, recall, and F1 score. On the x-axis, we have the different detection models. And there are three different colors for F1, precision, and recall. So talking first about deep learning, I tried to compare or like see if deep learning performs specifically better for a specific return of the LiDAR. So when I'm talking about LiDAR, we logged the LiDAR data into the images specifically for two formats. The first one is the DSM returns of the LiDAR, and the second one is the intensity return of the LiDAR. So talking briefly about it, intensity returns is basically the return from a specific object, and it depends on what it is getting reflected from. DSM is the maximum elevation within a pixel, and our pixel size was 5 centimeters. For this experiment, we can see that all of these methods perform similarly. Like they perform pretty well, all of these, but there's hard to see a difference between these models. The F1 metrics for all of these models was around 0.87, which is considered pretty nice. The other models I am explaining now is the OpenCV models. The background subtraction and frame differencing models performed a bit worse than the deep learning models, and that's pretty visible from this. The third model, Percept, performed better than the OpenCV models, but a bit worse than the deep learning models. So what caused the failure in detections? What caused the errors in detection? In this slide, I'm trying to find out what were the major error sources. So I looked into each individual slide and I saw what I had labeled and what the model had detected. So the manually labeled points are shown in blue, and the the model detected points are shown in orange. So one of the major error sources was people who were lingering around furniture. As they went, as they walked through the area and went to a furniture and stood still, the models failed to detect that. The second error source was the inadequate coverage over the northeast corridor where a single sensor was only available. Other sources of error for the deep learning and the OpenCV included atypical shapes and size of point clouds. For Percept, there were other sources of error, including detections on the staircase. The staircase was a peculiar object in our study space because it was 3D and we had projected our LiDAR data into 2D. So visualizing the elevation aspect of it was pretty difficult for the raster-based models. But Percept was able to detect people moving through the staircase. Also, as Percept worked real time and we were generating the rasters post-processing, there was some minor misalignments between the raster-based point clouds and the detections from Percept. They are there, but slightly they are off of their actual position. A final error I'm talking about are the false positives from a single source. A single person was sometimes detected as multiple people because of the LiDAR signatures generated from them. So I wanted to see how these error sources were distributed spatially across the space. I wanted to see if there was a spatial pattern, if a specific zone in the area was more susceptible to errors. And I plotted all the detections of false positives and false negatives into this image. So one thing that's clearly visible from this is that deep learning had the least amount of false positives and false negatives, while Percept and OpenCV have a fair amount. Also, the generic trend of false positives and false negatives for OpenCV and Percept were pretty similar. You can see that they attain the same shape. One thing I want to talk about here is for specifically OpenCV, this space to the northeast corridor, which is used heavily as an entrance space, has minimal amount of false positives and a very high amount of false negatives. This can be attributed to OpenCV's inability to detect people unless they are in the space for a certain time. I also use the different models to detect people in further frames, and this was done for the month of September. Running all these three models was pretty computationally expensive, and for the month of September, I wanted to see what is the space being used for, where are the hotspots and where are the cold spots. This slide shows you basically the same idea between these three models on where the common hotspots are. People are using this already a lot, and people are going into this space. One thing I'd like to mention is OpenCV has detected people, but it failed to detect people in the peripheral region of the study space. Another analysis I conducted was the temporal analysis for the month of September. I wanted to see if specific hours stand out in terms of activity. On the y-axis, I'm showing you activity that goes from minimum to maximum. On the x-axis, we have different hours of the day. As expected, the night hours were the least active, while the midday hours were the most active. Specific key points from this graph, I saw the first peak of the day at 9 a.m. And that's probably people whose class starts at 9. But you also see a small dip after that. And this can be attributed to people who can have slow mornings if their class does not start at 9. One other thing I'd like to talk about here is how all of the models are pretty similar for detecting activity throughout the day. But one section where it falters is like between the hours of 3 and 6. The Percept model says there is more activity than the other models. And This can be attributed to the fact that Percept used the three-dimensional data from that space, and it was also able to identify people who were sitting on furniture and only minor movements were observed. But the other two models that use the orthographic rasters were not able to detect it. Talking more about the temporal distribution, I looked at certain days in September and try to see what's the activity level. So I look at the first 14 days of September, and one thing that got my attention was the 3 day span of minimum activity. And upon inquiring, I saw this was the Labor Day weekend, where the students probably left for a vacation or something like that. So one thing I want to talk about how I did some analysis for the month of September. You can see such important subtle information about that space, how people are using it throughout the hour of the day and throughout the days of the month. So on my efforts to understand human movement and occupancy in the space, I compared 3 different models to see if a LiDAR-based model could be used to understand an indoor space. For the different models, deep learning was the most effective for the detection of human movement using LiDAR data. OpenCV's performance was hindered by flickering noise. This is the noise that's observed when rasterizing the 3D point clouds. Percept was effective at both tracking movement and stationary individuals, as well as the three-dimensional aspect of the space, including the staircase. Deep learning struggled at detecting stationary people despite specifically training for it. A hybrid detection model combining the strengths of all these models, because each model has its own benefit, going from detecting people that are moving in the space to detecting people that are stationary in the space. So that's where I'd like to end my talk today. Next, I want to share some pictures of me giving presentations of the work. And this includes poster presentations at OGIS 2024, at CDAG. I also did a virtual presentation at the American Society of Photogrammetry and Remote Sensing. I also did a OGIS poster last year, the Alumni Weekend, and I also attended the Spark Digital Twin Workshop, where I give a lightning talk at Arizona State University. A few other pictures I'm showing here of today, just the memories I gathered in the last 2 years. And I just want everyone to know this has been an incredible journey. And thank you so much for being there with the smiles and the support you have given me. And the boring slide, the references, they're always there. And I have more references, but I just chose to keep the key references that are in the slides. And I'm ready for questions, comments, or concerns. Thank you so much for your attention.